off with molar enthalpy of formation. That's we talked about this yesterday. Molar enthalpy of formation. Okay, y'all watching. Unfortunately, as useful as this is to do an individual compound made from its standard state elements, this doesn't happen very often in the real world. I don't fill up my carbon dioxide fire extinguisher by burning graphite and turning it into carbon dioxide. It's just not the way you do it. You don't make hydrochloric acid, you don't make HCl from taking pure hydrogen and pure chlorine and putting them together. It just doesn't happen that way. All right? We often have to do things in series of steps. Okay? And that's why we need to be able to use these and in something called Hess's Law of heat summation. Okay, that's what the next topic is. We're going to put those guys together and do equations that actually are useful for the real world. Because for the most part, we don't do molar enthalpy of formation equations in the real world. Now, the nice part about this is it doesn't matter how many steps it takes to get to your final product. You can tell by the title here, summation, you can add them up. You could do the same reaction in a series of steps. I mean, that's exactly what your body does, right? I can burn sugar. I can combine sugar with oxygen and burn it. I did that in Chem 1 as one of the early demos I did to show you about a reaction. You're burning sugar right now, okay? But you're doing it in a series of steps, okay? Going through the Krebs cycle and all that stuff, right? And at the end of the day, you get exactly the same amount of energy out of it that I would get if I burned the sugar outright, okay? So that's all that Hess's Law is saying. The enthalpy change of a reaction is the same whether it occurs in one step or in a series of steps. And this is good for us because now we can do calculations that are useful. Like I said, I added a few slides onto here just to try to hopefully make this a little clearer because I kind of used to gloss over doing the individual reactions here and adding them up longhand because I wanted to get to the using the back of the book, that chart I've given you on delta H's of formation, where you can actually use them doing chemical reactions. But I realized that you're going to see these kind of problems in the AP exam, so I needed to do more practice on them. I've always done some. I just wanted to do more on it. Okay. So let's start off with this. I want to start off with just, in general, a little bit of the theory behind this, okay? Look at this equation right here. Look at these equations. Can you tell me if I took all those equations, what they would add up to be? What would the end sum of those equations be? A and B are coming together to make C and D. But C is used again, when it reacts with G, to make K and B. D and R make G and T. What can I do? And you can think of this almost from your algebra classes. Remember your algebra where you had variables on both sides of an equation? Right? Weren't you able to do this in those kind of problems? I think you all remember doing this in these kind of problems. You're able to say, okay, I've got a C here and a C there, so he cancels out, right? Remember doing that? I've got a G here and a G there, so he cancels out. Anybody else cancel? The D, the B. So what is my overall equation? A plus R yields K. You never did that? Seriously? You guys, with variables, X and Y, seriously don't remember doing this when you summed equations up? I see half of you nodding yes, and the other half saying it's like you've never seen this before. Well, either way. Whether you have or not, do you all agree that makes sense anyway? Okay. Well, here's the thing, guys. Watch. Sure. Yeah, sure. All right, here's the thing. That's all. Forget about the algebra part. Forget about that. This is what's important. Look here. Maggie. Look. I had to say your name on TV. Now you're on YouTube forever. Until I tape this again because it doesn't work. What I would do, if this is the amount of energy X for this first equation, and that's the amount of energy Y that's given off or absorbed in that equation, remember, these can be positive or negative. If I sum them all up, I will get the total amount of energy if I were to have just taken A and added them to R and gotten K and T. So if it happens in a series of steps, if it happens in one step, same basic idea. There are problems with this, though, as you'll see when we start to do some of the examples. And we'll get to those now. All right, so we already have those notes. Okay, let's do an example. Let's use a real example, not A's and B's. Let's take that equation, and we'll do it backwards. In the previous one, I do several steps to make a final equation. Here is your final equation. Can I break him down into molar enthalpy of formation equations, which I've already taught you how to do? Yes, and that's what I'm going to show you what to do now. We're going to take each one of these compounds and write the molar enthalpy of formation equation for him. Okay? So what is the molar enthalpy of formation equation for C2H4? You all agree, if I were to make C2H4 from his standard state elements, okay? By the way, I still think sometimes people aren't quite getting this. Why is this not a molar enthalpy of formation equation? Why can't I just look in the back of the book at C2H5OH, look up the energy it's given off when that guy's formed, and write that down as the answer? Because these guys are not standard state elements, are they? So I'd have to have started with standard state elements. So let's make these guys from their standard states, all three of them, okay? We'll start with the C2H4. You all agree, if I made him from his standard state, he would look like that. Sorry, write that down. He would look like that. Write that down before you write the first example. You all agree that that's what he would look like, though, right? I take pure carbon, pure hydrogen, get C2H4, there he is. And I'm keeping the states and all that stuff. And if you look up in the back of the book, all I'm writing over here is a delta H. The delta H for this equation is 52.3 kilojoules. So when 1 mole of C2H4 is formed from its standard state elements, it takes 52 kilojoules of energy to do it. It's endothermic. Okay? What would the molar enthalpy of formation equation look like for water? I think everybody would have that one correct, although this time we're going to have to use some halves as part of our equation, as part of our coefficients. You all agree that that's what he would look like if I did him? That makes sense from yesterday? Should. We're allowed to use a half because we're not talking about a half of an atom, but rather a half of a mole of atoms. So a half a mole of oxygen, 1 mole of hydrogen gives me 1 mole of water. Makes sense. And when you do that, you release 285 kilojoules of energy. Almost there. I got one more to do. I got to do C2H5OH from his standard state elements and see what happens with him. To make him, again, I'm going to take pure carbon, pure hydrogen, pure oxygen, balance it out, should look like that. By the way, I left out the little G here after oxygen. I kind of ran out of room, as you can see. I don't have a whole lot of room here. It should be a G after the O2. Kind of make that guy smaller to begin with. All right, now you might think to yourself, but you would be wrong, that I could just add these 3 guys up now. I cannot. Why can't I? I told you there's going to be a couple of twists. This is the first twist. In the previous example I gave you, which uses ABCs, R's and T's, everybody was written out the right way. What's the problem with these guys? These are molar enthalpy of formation equations. Did I form water in this equation? Did I form C2H5 in this equation? I broke them up. I did the exact opposite of forming water and the exact opposite of forming C2H4. What will I have to do to equations 1 and 2? What will I have to do? I'm going to have to reverse them. And when I reverse the equations, what do you think is going to happen to these numbers? Opposite side. Same exact amount. I don't care, guys, if you form water from its standard state elements or if you break water up into its standard state elements, the value for the delta H will be 285. It's just a question of whether it be positive or negative, whether you're absorbing that much energy or you're releasing that much energy, okay? So let us reverse those first two, because they are not being formed, they're being broken up. But we'll keep this guy the same, and then we'll add up the numbers. Now, I know it's a lot of writing, and that's why I'm not going to make you write another example like this in your notes, or even in the homework, because you have to write it all at once, you got to write it all out again, reverse. I know it's a pain. I understand that. So I'm not going to make you do this. But I am going to show you another example in a little bit of how you do these. Because there's a second twist to it. There's one twist is you sometimes have to reverse equations. Guys that aren't being formed. Not sometimes, almost every time. I think there's very rare that you won't have to, at least in one case, flip a guy around because you're trying to break him up instead of form him. So here are the same three equations, reversing the first two and keeping the third one the same. I know it's a pain, but you got to write it all down. Once you get that all copied, just like you would in an algebra class, just like you did the last board, are there guys I can cross out that appear on both sides? In other words, they've been formed and then they've been used up again. Sure, there are a lot of guys like that. Let's take a look. Do you see carbon on both sides? Right? So, 2 carbons there, 2 carbons there. That's nice. They're gone. Don't have to worry about him. Who else appears on both sides? What other guy? Who? The O2, right. Okay, I got a half of an O2 over here. On the left side, I got a half of an O2 on the right side. By the way, you say, well, don't they both? No, because the arrow is there, so he's on the left. The arrow's here, he's on the right. So they cancel. Anybody else? Cancel? I see somebody. Yeah, of the H2s, I've got 3 on this side. Do I have 3 on the other side? 1 there and 2 there. You see it? So they all canceled. Well, geez, all that stuff is canceled out. What do we have left? Just him. Don't circle these, but just him, him, and him, which is exactly what I wanted. Right? So when I go and add these guys all up, that's what I get. Isn't it? Pretty neat. Now that I've changed the sign, did you notice I changed the sign for the first two? Opposite sign from what they were a minute on the other board. Okay? Why? Because they weren't being formed, they were being broken up. Now I can just add them up directly and get that number. And that's the correct answer. Isn't that cool? Now, if you think that's cool, I know you don't, but if you do, wait till you see what I'm about to show you something here. It's pretty awesome. We just got doing this whole problem, right? And I'll bet you no one out there realized what I was actually doing. Let me show you. Is there another way I could write this same equation? Like C2H4 plus H2O yields C2H5OH. Don't write this down. Don't need to copy this. Could I write this differently? We had organic. Does that look familiar to you? That's an alkene reaction. It's a hydration of an alkene. Markovnikov's rule. All the stuff we talked about with organic chemistry. Adding an OH across the double bond. Right? Ethene, ethanol. Did you know? While you were doing that problem, Did you recognize, oh, yeah, that's that thing, and I'm going to make ethanol out of this? No. We always have blinders on. We have blinders on when we're doing a problem. It's like we can only see what we have in front of us, and you can't do that in AP Chem. In AP Chem, they're never going to give you a problem in the free response. That is just one thing, just one type of problem. It's always going to have multiple facets to it. So you know what they're going to do in the introduction to this kind of problem? They'll say the alkene ethene or whatever ethene, maybe they'll choose some other one, reacts with water in a hydration reaction, and they're going to put a lot of extraneous information in there that's going to try to confuse you. Okay? And they make ethanol. Now, people who have it at organic are going to be even worse shape than you guys because they will use, a lot of times, they use organic compounds as their examples. And there's many people who take AP that they cover almost no organic because there's virtually no organic on the test. But you should be able to see that. You have to be able to see that. Don't get confused by that. By the way, you know what you're going to learn after the AP exam? I cut that section out until afterwards. You're going to learn how this guy happens, the mechanism by which this happens. And it's called electrophilic addition. And it looks like this when you break it down. Yeah. Fun times. So all of this is organic stuff that we will or already know. And now we also know how to take that same equation and figure out how much energy would be given off when you did it, or would be released, or would be absorbed, either way. Isn't that cool? No, it's not. It's confusing. It's incredibly confusing. I know that. I realize that. But you have to get used to it. Okay. Now, do not try copying this. There's too much to copy here. But I found this online. I want to go through another example because there's a second problem. Besides the fact that you often have to reverse problems, there's another problem. Maybe you can see what it is. Take a look. Without copying it, you are going to get lots of these. Tonight's homework, 32 to 37, every one of those is just like this. So you want to know how to do this without me actually writing it into your notes because it takes forever to copy, as you'll see. Okay? You don't really want to copy all this. All right, so look at this. Let's say I gave you this on the test, or the AP question gives you this, and I'll guarantee you will see them like this. It says, find the delta H of this reaction given these delta H's and these reactions. Wow. Okay, that's a little complicated. Can you figure that out? I want everybody to stare at it for a little bit so you can figure out how I can get this from these. Let me ask you first. Is there a way I can get N2, two N2s on this side? What equation will I have to use? The third equation has N2 in it, doesn't it, right? So, okay. And its N2 is on the left side. Beautiful. What else is on the left side? That also helps me out, that I also need for this equation. Oxygen, but there's only 3 of them, but that's okay. There's only one N2 here. So these other guys, I don't want them, but that's okay. We do that guy first. But what will I have to do to equation 3 in order to have 2 N2s? What will I have to do to him? Multiply everything by 2, right? Including that number. Got it? So, again, you're not copying this, but 2 times equation 3 is going to give you 2 N2s, which is nice. I now got my 2 N2s. Unfortunately, I also have 6 O2s. I don't need that many. We'll take care of him later. H2s, which I don't need. HNO3s, which I don't need. But nice, I have taken care of at least 2. Oops, all that stuff's still up there. I've taken care of at least, I've gotten this guy, he's all done. And I've got some oxygens there, but not the right number yet. What do you think I should do next? Who else do I have to make? N2O5. What equation will I need to use to make him? What's the problem with the second equation? Anything? It's the wrong way. You see why the second equation is the wrong direction. Second equation, N2O5 has to be on this side. And I need 2 of them. So what do I have to multiply this guy by? -2, right? I got to take 2 and then also take the opposite of that sign. You see what I'm saying? So watch. So -2 times equation 2 gives me this guy. All right, I'm good now. I got him. I got him. There he is. I got him. There he is. I'm almost there. I'm missing one guy, though. Who I miss? I have oxygen's not correct yet, is he? Okay, how am I going to get oxygen correct? Well, by the way, have anything, as we've gone along here, has anything canceled out? What things have canceled out already? Let's see. 2 H2s have canceled? We have second, and we've only used these two. Where do you see 2H2 in both places? But we haven't used the first one yet. That's not what I'm asking. I see what you're doing. I see you're skipping ahead. I'm asking you, so far, has anything canceled out?
Yeah.
What has? 4 HNO3s, okay? They've canceled out, okay? But I have a couple of problems. I got water, which I got to get rid of somehow because he ain't in this equation. And I've got an extra oxygen. What should I use, Anthony? What equation? Yeah, the first equation. Because I've canceled out HNO3. All right, now I'm going to use the first equation, and I have to take the opposite of it. You see why? I want to have one less oxygen over there, and I want to get rid of that water. Now everything cancels out. By the way, it did not put a line. I found this one online. And what did they forget to put a line through? Yeah, they forgot to put a line through that. Okay. So what's left? Well, what's left is 2N2, 5O2 yields 2N2O5, which is exactly what I wanted, correct? And what do I do with that? I add up these numbers, and I get the final answer, which is 59 kilojoules. So is this reaction endo or exothermic? Endo. Okay. Beautiful. That is what you have to do. Now, so what was the second problem with these? The first problem was sometimes you have to reverse them. And you saw that in this as well. What was the second problem? Sometimes you're going to have to multiply or divide by some coefficient for the whole thing. Okay, 2 or 3 or half or whatever. All right, your homework is page 597, numbers 32 to 37. Okay?